Okay, the screencast is on an honors chem level of electrochemistry. So this one, we're just going to kind of look at some of the vocabulary we're going to need and how to do some of the particular problems that we're going to encounter in electrochem. Again, on an honors chem level. So electrochemistry is the study of chemical reactions that either produce electrical current or use an electrical current to force a reaction to happen. These are all reactions that involve oxidation and reduction, or those redox reactions. So since those types of reactions involve a transfer of electrons, they are the ones that we use with electrochemistry. Now, the electrons move from the substance that is oxidized to the substance that is reduced. And this flow of electrons is that electricity. So a couple of things that we need, or terms that we need to know. We're going to talk about electrodes. And when we talk about electrodes, there are two types. There's the anode and the cathode. You need to be very familiar with what goes on at each of those electrodes. So an anode is the electrode where oxidation takes place, and the cathode is the electrode where reduction takes place. Now, I kind of have a way to remember that. There are two animal names in this. There's a cat and an ox, and those two cannot be together because that's just wrong. Or, if you want to look at it another way, is the two anode and oxidation, both of those start with a vowel, they go together, and cathode and reduction both start with a consonant, and so they go together. Either way you want to remember it, as long as you remember it. Okay. Anions move toward the anode, and anions are negatively charged ions, so they're always going to move toward the anode, and cations move towards the cathode. Sometimes in chemistry we make things hard. This is not one of those cases. So it's very, very easy to remember, and it's going to be very important for you to remember. On the AP chemistry level, you're going to be looking at a lot of particulate diagrams, and you're going to have to show which way the electrons are going, which way anions, which way cations are moving in an electrochemical cell. So this little bit of information will help out a whole lot as we get into looking at those diagrams. An electrochemical cell is a system of electrodes and electrolytes. So we're going to be looking at ionic solutions in which either a chemical reaction produces electrical energy, like in a battery, or where an electric current produces a chemical change. So in that case, we're going to be hooking up a battery to a chemical reaction and forcing a reaction that normally would not occur to occur. Now, we have different names for these. So we give one name to the electrochemical cell that produces electrical energy, and we give a different name to the one that uses electrical energy to do something else. So here they are. The first one is a voltaic or galvanic cell. These, I like to use the word or the term voltaic, but I think more and more you're going into galvanic in AP. So make sure you're familiar with both. This reaction happens spontaneously. So it just happens on its own if we get these two chemicals together and electrodes, and it serves as a source of electrical energy. So these are our batteries, and batteries produce volts. So both of these, voltaic's very easy because it produces volts, but galvanic also has a V in it, so that this is the one that produces electrical energy. So any of our batteries are going to be voltaic cells. The other type of electrochemical cell is one in which we use an electrical current to force a non-spontaneous reaction to happen. And those are called electrolytic cells. An electrolytic cell, electrical energy is required to produce the redox reaction. So we're using electrical energy to force a non-spontaneous reaction to occur. This would happen in electroplating, so like gold-plated jewelry. Gold normally doesn't run up to other metals and stick to it. So we actually force that reaction to happen with electricity. Now, rechargeable cells like a car battery, when they are recharging, they function as an electrolytic cell, but when they are starting your car, they function as a galvanic cell. So they actually have both. All right. Now, when we talk about these types of cells, we're going to be calculating the electrode potential. And the sign of our electrode potential will let us know whether a reaction is occurring in a galvanic cell or an electrolytic cell. So electrode potential is the difference between an electrode and its solution and can be calculated using this little equation right here. So E cell, which is your electrode potential or cell potential, it's also called electromotive force. So any of those terms, you've got to know that that is E cell, is equal to the potential of the cathode minus the potential of the anode. Now, I like to have this kind of both ways. And so if we think about it, what process happens at our cathode? Well, that is reduction. And the process that happens at the anode is oxidation. So we could also read it as our cell potential is equal to our reduction potential minus our oxidation potential. Again, that's where I got this information from. Anode is where oxidation takes place. Cathode is where reduction takes place. If E cell is negative, the reaction is non-spontaneous and will not occur in a voltaic or galvanic cell. It's going to occur in an electrolytic cell, and we're going to have to force that reaction to happen. So if E cell is positive, the reaction is spontaneous and it will occur in a galvanic cell. So it's important to remember your signs there. So if we're looking to find the electrode potential, then we're going to be looking at, we're going to need to identify what's going on in this particular reaction. So here I have a nice little reaction. It's a copper-silver battery, or at least electrochemical cell. We'll see if it's a battery or not. And so we need to identify what's going on. So we have copper 2 plus going to copper 0, so copper metal. So what's going on here is the oxidation number is going down. So this is my reduction. And for silver, it's going from silver metal to silver ion, so 0 to 1 positive. So this is my oxidation. Now, I'm going to need some values so that I can work with this equation up here. And we're going to get those values from our standard reduction tables. Now, I'm going to show you a full table that has just a lot of reduction potentials on there. On the AP exam, they're not going to give you a giant table and you'll have to hunt. They'll give you a selection of reduction potentials, and you have to choose the appropriate one or ones. And there will be some distractors in there. So it's just on a much smaller scale than what I'm about to show you. All right, let's go to my electrode potentials. Here we go. So this would be some standard reduction potentials, and that's what it's labeled here. We have our values. They will be given in volts, so every single one of these numbers has the unit of volts. Now, every reaction on here is a reduction reaction, and that's why it's called a reduction potential. So we have to find values for both reduction and oxidation. So what we're going to do, all of these are reduction potentials. The reverse of a reduction potential is its oxidation potential. So in this case, we are going to be looking at silver and copper. Now, in our particular reaction, we're looking at copper going from copper 2 plus to copper. We also have one with silver, and silver, oops, didn't mean to go there, or silver ions and silver metal. Now, one of these is written in reverse, and that would be the oxidation one, and that can really help you remember what's going on here. So if we're finding our cell potential, it is equal to our reduction minus our oxidation. So previously we looked at our electrochemical cell, and we had copper being reduced and silver being oxidized. So we're going to go back to our reduction potentials, and copper was being reduced and silver was being oxidized in the reaction we had written. So now we're going to look at these values. Copper was going from copper 2 plus to copper metal, and that is 0.34 volts. Then I'm going to subtract the cell potential for oxidation. The reason there is a subtraction sign in here is because this reaction, as it's written here, is the opposite of what we need. We need silver metal going to silver ions, and this one has silver ions going to silver metal. So this negative sign that's built into the equation will account for that. So this reaction is the one that's written reverse, and we'd expect that because it is an oxidation reaction, not a reduction reaction. So we're still going to put this number, so 0.80 volts, and then we can figure out our cell potential. So it's going to be negative 0.46 volts. This is a negative value, so that means that the reaction is not spontaneous and will only occur in an electrolytic cell. We're going to have to force this reaction to happen. So this won't be a battery. This one we have to use a battery to get this reaction to happen. All right, so that's the very basics of what's going on and how you find an E cell or a cell potential for a reaction. All right, so, and there's the work for that one. All right, what I would like for you to do is you should have access to the reduction potentials, and it would be, if you can print those out or just have them pulled up on another screen, I would like for you to try these three. So go ahead and pause this screencast so that you can do that work, and then I'll come back and you can restart it and I'll give you the answers. Okay, so after you've done your work and found your E cell for each of these, I got my electrode potential for A to equal 2.23 volts. So this one is positive. That means this reaction is spontaneous. That means the reaction will occur in a galvanic cell. For B, my E cell is 1.26 volts. Again, it is a galvanic cell. It is a spontaneous reaction. For C, I ended up with an electrode potential or cell potential of negative 2.29 volts. That was supposed to be an equal sign here. So this reaction, E cell, is negative. That means it is a non-spontaneous reaction and will only occur in a electrolytic cell. Okay, another thing that I would like to point out is if we go back and just look at A, B, and C and just the reactions that are given, especially as we're going into this next chapter from ions in aqueous solution. If we look at reaction A, this reaction is completely balanced. And we have it balanced for mass on both sides, and we also have it balanced for charge. But if you look at B on the surface may appear to be balanced because we've got it balanced for mass. But this guy is not balanced for charge at all. We have aluminum, which is going to be gaining 3 electrons, but we have potassium, which is only losing 1. So where did all the electrons come from? Well, this is just an unbalanced equation. It's going to take more of one of these. So if I split this into my half reactions like we did in the last chapter, we've got aluminum going to aluminum metal, and we have potassium metal going to potassium ions. Well, we balance for mass, oxygen, hydrogens, and charge. So I need to have 3 electrons over here. That's how many are being absorbed here by the aluminum. But potassium is only going to release 1 electron. So that means I have to multiply this whole reaction by 3. 3 and 3. Now my electrons can cancel out, and my balanced equation for this is 3K plus Al, 3 positive, yields 3K positive plus aluminum metal. And that would be the balanced equation. Now, this has absolutely 0 effect on your electrode potential. It is going to be exactly the same. So even though we had to multiply our potassium by 3 in order to get a balanced equation, it does not affect your electrode potential. So don't mess yourself up and think that it does.